Today we're going to talk about two things. I want to finish gossip. Remember we saw gossip last time? Today I want to show you a pretty sophisticated gossip algorithm, doing some real work, doing something very non-trivial, topology management. And the algorithm is not so simple, even though it's still in the gossip framework. It's doing some stuff, and we'll see how it works. There's also an article on the algorithm called T-Man. There's a PDF of the actual scientific article, so this is a summary of that on Moodle, if you want to look at. And if my explanation is missing some things, you can find more details here. Then I finish with some interesting little thing about fireflies, heartbeat synchronization. That gossip sometimes happens in nature, okay? It's not just in computer systems. So that's the first part. The second part is another kind of gossip algorithm called content distribution, which is doing also something non-trivial, and it's doing something that has a new idea. It has to give incentives because the nodes are selfish nodes. Each node is doing something. Basically, we want to do file sharing, okay? Legal file sharing, of course. File sharing. But the nodes, once they have gotten the whole file, they have no reason to stay, right? So they maybe will shut off. So we want to encourage them to stay. So there's some new idea here, which is not in the standard gossip. We have to somehow encourage the nodes to stay. So there's something in there for that. So there's a famous algorithm called BitTorrent, and still many variations are used today. Okay. First, a few words for the Ukrainians fighting for their freedom and for our freedom. Okay. So first I want to show you this one. So now we're going to go to a more sophisticated gossip algorithm, but it's still this framework. Okay? Remember, we have an active thread and a passive thread, and it cycles, maybe every 50 milliseconds or something. So there's a wait. You select a peer, then you exchange data. You send your state, you get state, and you do local update, and the same guy, this guy does the same. So the passive thread is just waiting for messages. Okay? So that's still the same framework. So last time we saw already an interesting algorithm, which is network size estimation. Okay, that was already very interesting, but now we're going to go even and see something even more sophisticated. This one is actually really used, okay, in cloud systems where they have to build up from scratch. So the topology management can create a beautiful connected network with some nice structure, starting from random nodes. Okay. So, for example, we have nodes that are connected randomly. So, a bunch of nodes connected some random way, but we want to connect them in a very beautiful, nice way. For example, we want each node to have 4 neighbors. Okay, like this, for example. We want this structure. This is what's called a torus. Okay? So we want this structure, but these 9 nodes are randomly connected. So each node has to find the good 4 neighbors among who knows where these are? And normally these neighbors are ones that should be close to the node. So this topology should somehow, these 2 nodes should be nodes that are close by in the real world if we want efficiency. So we want to take nodes that are randomly connected in some weird way and convert it to this nice thing. Okay? So that's what the algorithm does. And it's considered to be as a service. That means any program can use this algorithm to bootstrap the structure. So any distributed system. Okay? And it's very general. And it's based on a ranking function. So we have some function that tells you what is the distance between nodes. Between any two nodes, it tells you what is the distance according to whatever you want to invent. Maybe it's like the real world distance or something, So you give it its parameter. And I'm going to show you results for some typical structures, a ring structure, a torus, which is like that one, it's a square where you connect the opposite ends, binary tree, and you run the gossip, and by magic, the random network transforms itself into this beautiful structured network where the close by nodes are also neighbors in the structure. So it's very nice, okay? So this, and it's practically useful. We showed already previous things, failure detection, resource monitoring, aggregation, but T-man, this one's called T-mana, you can use it to jumpstart other protocols. If you want to build a distributed system, this algorithm creates order from chaos, in a sense. It builds the nice structure from some random mess. So it's really nice algorithm, okay? Okay, so what is the problem? So I'm going to make a simple mathematical definition, and I'll try to give you intuition, okay? So we have this random mess. So you have n nodes. Each node has neighbors, and we say it's a view of size C. So it has C neighbors, 100 neighbors, for example, and it's called the view. So the node has a view, okay? It also has information, profile, used to calculate the ranking, okay? So it starts with this distance function. Given any two nodes, x and y, you can calculate the distance between two nodes. Now I can take this node, x, this node y, and I can calculate what is the distance. Right? And here, for example, I want the distance to be 1 or to be small or something. But here, I mean, the nodes are just sort of randomly connected with distances. So the distance is not really nice. So the algorithm has a more elaborate thing called ranking function. But it's built from the distance. So if I have node x, and I'm looking at these nodes, other nodes, I want to see which ones are close to me and which ones are far away, okay? So the set of all orderings such that they're increasing distance, okay? So if I have a bunch of nodes, so I have a node x here, you have y1, y2, y3, y4. Well, this ranking function will order them so they're in increasing distance, okay? So for example, it might be y4, y2, y1, y3. These are increasing distance. But there's other ways to order them, possibly, okay, of these orders, because we're not always, it's because of this distance function, okay? So now we can define the problem. For every node x, find the closest neighbors among all the nodes according to ranking R. So the ranking R is defined so that if this is node x, then these nodes will be the closest, okay? And for every node, it will find the closest. So we need to construct a view. So instead of some random view here, we have this very organized view, view x, such that R, all the nodes except x, contains a ranking that starts with view x. So that means that view x is following the distance, the increasing distance, okay? So that's basically the specification. So how are we going to do it? Well, it's kind of like aggregation. We're going to keep running, and things will get better and better and better. Okay? So here's the code. So this code, this is actually images taken from the paper. So there's a slight variation of the framework. So I have an active thread and a passive thread. So the active thread, it selects a peer. So this is an important function. Which peer does it select? Well, somehow you want to select one that's already kind of close by, okay? Okay, and then you have my descriptor, that's me. So you have a buffer, which is the view plus the node itself. I send it to P, and then I get another view back. So I have two views, okay? My view and the one that comes from the other side. So it's view, which is mine, and view P is the one I've received from P. And these two views both have size 100, for example. And then I merge them in a smart way. Okay, so I combine them, and I select a new view out of that. So this new view updates the view. So basically, the idea is that if I have 200 nodes, 100 in each view, I have to reduce it to be 100, okay? Because I only have 100 here. So I have to smartly pick the ones, okay? And the other side, the passive thread, basically does the same thing, okay? So it waits for the message from the active thread. It again does the same thing, and it does a merge, and it does a select view, okay? So we have to define these smart guys. It's mostly select peer and select view have to be kind of smart according to the rank, okay? So here's the idea. So initial view and merge are very straightforward. So initial view, I have just some random whatever connection. Merge is just a union. So merge would have 100, 2 plus 100, 200 nodes. But these two guys, select peer and select view, are smarter. Okay? Select peer, okay, I have to, which neighbor do I talk to? Well, the idea is I want to talk to a neighbor that's kind of close by. I want to make this thing converge to this. So I don't really care so much about far away nodes. I care about close by nodes. But still, I have to be careful. If you take the current view, which has 100 nodes, and you rank them according to distance, then you don't want to pick the actual closest one, because that limits your vision. You still don't really know where the true closest one is. So if you immediately start by picking the one that you think is closest now, then you're limiting too much your view. So that's not good. But still you want to kind of look at close by nodes. Okay? So you take a random node from the first half. Okay? So the current view, 100 nodes, the first 50, the 50 are closer than the next 50. So you take a random one from the first half. So it's kind of a close one, but it's still a bit random because you still don't really know where the true closest one is. So you don't want to too much limit your vision, okay? So that's how this one works. Why is it like this? Well, if you do like this, it works pretty well, okay? If you change this, then maybe it won't work so well. And the second function, select view, here the buffer has 200, combination of 100 plus 100. So this is very easy. You rank these 200, and you pick the 100 closest ones. That's pretty easy, yeah? You pick the 100 nodes that are closest. So basically, it's like casting a net. You talk to a random node, and that node sees other nodes. You pick that node's view and your view, and you pick the closest ones. So that means you're kind of gathering the closest ones to you, the ones that are according to the ranking, the topology you want. Okay, so the ranking is very important. Okay, so let's say, so here's some typical examples. So the ranking is defined starting from this distance function. So you need to define distance, okay? But distance is kind of very straightforward. Here it would be Manhattan distance. So distance between these two would be 2, for example. But on a line, if you have a line of nodes like this, if I want to do a line, the distance would be the difference between the two positions, but an absolute value, because it's a distance that's positive. But if you have a ring, then you have to be a little bit different. If you have a ring, then these two are connected together, and then you have two numbers. You have A minus B, but you also have the other one, N minus A minus B. If the two nodes are very close to the edge here, A prime and B prime, they're also very close, even though this number is very high. It's almost N, because there's N nodes, but because it's a ring, they're actually very close. You see? So if you want to do a ring, you have to do something like this. And from this, you can define the ranking function, okay? Or you have a mesh. The mesh is like a square grid. A torus is a square grid where you're connecting the opposite edges. Or you have a binary tree. But then you have the path on the tree. So if I have two nodes, if I want a path, I have to go up to the common ancestor, and then I go down to the other one. So how many steps? And if you define the ranking like that, the algorithm will automatically create a topology that looks like that. Okay? So here's an example. So this is a real example from the torus, which was tested in the paper. So you have, the nodes are randomly connected. So it's a mess. It's a cloud, okay? And this is what happens after 3 cycles. So you already start seeing that it's starting to look like a torus. So after 0 cycles, it's just a random cloud when you start. And the more you go farther, the more each node knows the ones that are closest to it, and the more it starts actually looking like a torus. Okay? So after 15 cycles here, you basically have mostly solved the problem. It's a complete torus. Okay? Of course, there might be a few nodes in here, a small number, that are still wrong. And that's tricky, okay? I mean, once you get to the very end and you have almost the torus, then you have to do another thing. So the algorithm has 2 parts. Active thread, and it picks the passive one. And I have another active thread, which picks another passive one. But this is a random number. This one, it actually might pick the same one. So some nodes, by some random chance, are chosen a lot, okay? And some nodes are not chosen so much. So the nodes that are chosen a lot, they will converge faster. And the nodes that are not chosen so much, they will converge slower, and they slow everything down. These slow nodes, they have bad information, and when you talk to them later, you actually might get things worse. So you want to make it so they're all converging at the same rate. So you make a small trick to the algorithm, a small change, so that they will converge at the same rate. Okay? So I will explain how that works in a minute. You can think about it. How would we do that? Well, it's a very simple idea. When a passive node gets contacted, and if you get contacted too much, if it's already busy, it can reject an active node. And if a passive node is not contacted, it will accept the active node, so it kind of balances it. Okay, so we'll see that in a few minutes. Okay, we can make some theoretical computations. Okay, so here I'm looking kind of at some different topologies. So for every node A, eventually the adjacent node B, so the one that's just next to A, has to be in the view. Okay, that's what we want. It has to come very close. So we can define for each topology what is the maximal rank. So here there's 2 nodes that have to be right next to A. Here there's 4 nodes that have to be right next to A. Here in the tree, it depends on which one. For the root, there's 2 nodes for A1. For A2, there's 3 nodes, the parent and the 2 children. And for A3, here, there's only 1 parent, okay, if it's a leaf. So those are small numbers, so the view has to be bigger than that. If we have a more sophisticated structure, if we have like a d-dimensional cube, then the number would be 2D. So if you have a 10-dimensional cube, we need 20 nodes, okay? So we can make kind of a very rough computation, okay? What is the probability that B, the next guy, is in the view of A after cycle I? This is a capital I. Okay, so I is the cycle number. This should be lowercase, I guess, huh? So when you start, it's C over n minus 1. So C would be like 100, n would be like 1,000,000. That's the total number of node system. So the probability is very small in the beginning that this node is right next to A. Okay. But if the rank is less than C, and that's usually the case. If C is 50 or 20 and the rank is 4, then we're good. So that's the condition. The view has to be big enough to hold all the adjacent guys. So for these topologies, it's okay if we have a view of 50 or 20. So if we take I, then it's 2 times the probability of I minus 1, because we're looking at 2 times as many nodes. So it's 2 to the I times the probability of 0. Therefore, the full probability is C times 2 to the I divided by n. Okay? And now we can actually compute the number of cycles. Okay? From this, P is less than 1. So it goes to, let's say it goes to 1, then I has to be less than log 2 of n minus 1 minus log 2 of C. So it's logarithm, but the C kind of makes it a little bit more efficient. The bigger the C is, then the fewer the cycles. But of course, there's an overhead also with big C. With big C, you have to store them all, you have to send them all over the network. But the bigger the C is, the I will be a little bit less. Okay? So basically, the number of cycles is logarithm. That's very intuitive, because each step is doubling. Okay? So there's some simulation results. So these are coming from the paper. So this is the proportion of embedded target links. So the proportion of links that are good, and these are the cycles. Actually, what's happening is it's multiplying by 2 each cycle, but eventually, when you get too many cycles, you start looking at the same nodes over and over again. You fill the whole network, it saturates. So this thing kind of flattens out, okay? And it's for different topologies. So the solid line is the ring. The one with the little triangle is the torus, it's almost the same. Then you have some other ones. Then you have it, whether it has balancing or no balancing, but that's not so important here. So it basically, our model multiplied by 2 is pretty good until the number of cycles reaches the final value. And then it doesn't work so much, then it flattens out. So here we have n is 2 to the 17. So of course you know how much that is. So how much is that? Now I want to see if you guys are really computer scientists. Powers of 2, man. This is almost like 130,000, right? Something like that. Or a little bit more than 1,000. C is 40. So if you do the computation, you get kind of 12, 13 cycles, okay? So here, the log 2 is 17. Here it's 5 or 6, so it's 12, 11 or 12. So basically, the limit would be here, somewhere, with these two numbers. So that's reasonable. If you now make another graph, where you actually define the convergence factor, how much does it increase in each cycle to the next? You see, our model says it should be 2. Well, it's kind of 2, 1.8, not too bad, until you start getting close to the limit, and then it goes down, of course, because you're saturating it. You're looking at the same nodes over and over again, eventually, yeah? So it approximates the predicted factor until the cycle where convergence is predicted, okay? Okay, now remember I talked about balancing. Notice this one, the little square, this is the binary tree. It's a particularly bad one. You see, it's bad, huh? But this is this balancing thing. So the fact that you're not adjusting that some nodes are converging faster and some are slower, this actually makes, it depends on the topology, but for the binary tree, it's particularly bad, you can see here, huh? Okay? So this is simulation results for this. Okay, so now I want to tell you how this balancing optimization works. Okay? Okay, so we saw rapid convergence phase converges exponentially. Yeah? It takes the logarithm of the number of nodes. Okay? Okay, but still we're not at the end. Huh? The final convergence time depends on the actual topology. At the very end, there's some left behind nodes, which we'll see in a minute. Huh? But the rapid convergence phase, we need to balance it. And what that means is that all the nodes have to converge at the same speed. If they don't, then some nodes will converge slower, and so the information they have will be worse. And when a fast converging node talks to a slow converging node, information will get worse. Okay, so it kind of pulls everything down, these slow converging nodes. Okay? Okay, so the way it works is that all nodes will count the number of times they've been contacted. So these are the passive ones. Huh? So the passive ones, they get contacted randomly by active ones. And some of them might get contacted more than others, but they can count the number of contacts, and they refuse connections if this number is greater than the current cycle count. It should only be contacted once per cycle, huh? Really, ideally, yeah? But because it's random, usually it's not going to be like that. There's going to be fluctuations, and some nodes are going to be contacted a lot by random chance. So if there's a node that gets contacted too much, it refuses another contact. So the active thread sends a message, and there's a refusal saying no. So the active thread has to pick another one, okay? And this is done using a ping, a 1-bit message, because this doesn't have to actually send the view. Huh? First you have to ask, can I send it to you? And the guy says yes or no, so it's 1 bit. Huh? And if it's yes, then you send the information. If it's no, you have to try another node. So if you do that, okay, you might think, well, it's more messages. Yeah, it's more messages, but the performance gets a lot better, as we will see. I'll show you a graph. If you do this optimization, then all nodes will be converging at the same rate. So they'll all be getting better at the same rate, and that's the best approach. Okay, so that's the rapid convergence with the balancing. But now, they're still at the very end now. At the very end, we're almost done. A few left behind nodes are not on the topology. So we have a torus, a beautiful torus, but there's like one node or two nodes that are wrong, that are in the wrong place, okay? that are not where they should be on the topology. So the random algorithm, it's not going to work so well, because the random algorithm, it's not really picking on that bad guy, the one that's badly placed. It will actually mostly look at nodes that are already in the right place, okay? So we need something else at the very end to handle those stragglers, okay? So the way to do it is the stragglers, how can they do it? If I have something like this, let me make a picture. If I have a straggler, okay? So here, let's say I have some kind of a square, but there's a missing link, okay? So here's some kind of a square thing. But the node that should be here is actually sitting here somewhere. But actually this one, according to the ranking, should be there. Okay? So how can it get there? Well, the only way is step by step. It doesn't have, it has 3 neighbors. So basically the only way it can get there is it moves step by step like that, like along the links that already exist. Okay? So the optimized endgame is actually doing routing. These stragglers, the bad guys, they're going to move along the good edges until they find their place. Okay? So instead of random selection of the peer node, okay, we have to do something else. Okay? We have to select the closest one. So somehow we have to select one that, okay, so this is maybe not explained very well. So we basically, if there's a node that's not correct according to the ranking, then it has to route, which means it has to do one step, okay? So these nodes are close nodes, so they will move step by step. So let me show you now a graph, how it works. So this is ring topology. So this is the graph coming from the paper. So here we're making a ring. That means each node originally was random neighbors, but at the end it has 2 neighbors, and the one that's there has it, that one plus another one, so it's an actually ring at the end. So again, here we have 2 to 17, c is equal to 40. Okay, here we're running different versions of the algorithm, a certain number of cycles. Okay, so here is the number of nodes that are wrong. Okay, so at the beginning, they're all wrong, 100,000, between 10 and 100,000. Most of them are wrong. And after a certain number of cycles, we get, so you see at the end is harder. Right? Here is one node that's wrong. And eventually it's 0, so it goes down. Well, it goes down infinitely, but we don't have to write that. It goes, so the 1 is the important step. Once it goes below 1, we're good. So we have different algorithms here. So this one is the totally naive one. There's no balancing. That means the nodes are converging at different rates. And no endgame. That means we keep going, even if the topology is perfect. Well, this one is very bad. Look, after 100 cycles, there's still 1,000 nodes that are wrong. Because it's just randomly trying to place them. Okay, it doesn't work. So we have to do balancing. So here we have balancing. But now, look at the endgame. Okay? Okay? Now, we have rapid convergence and endgame. If we start the endgame immediately from 0, okay, then we're preferring to route. But if the topology is very bad, the routing is not really going to work very well. So this one doesn't work very well in the beginning, but at the end it's okay. Here we have no endgame, we just have balancing. See, the end takes a long time. So here we are at 30 cycles, and there's 2 nodes that are wrong out of 100,000, okay? Oh, sorry, there's 3 here, and then there's 2, and then there's 1, and that takes 15 cycles. So if we have no endgame, the very end, so we have balancing here, but no endgame. You see, those stragglers are hard to catch, okay? So if we have both balancing and the endgame, then it goes down very fast. And when we're at the end, we have 1 node left, and it's very quickly moved to the right place. So you see the 2 optimizations are helping a lot, okay? Balancing and optimized endgame. You see, both of the optimizations are important. So if you just do naive gossip, you get this one, huh? It doesn't work very well. So you have to be a little bit smart for T-Man, huh? You can't just do naive gossip. So gossip is very simple, but you still have to do some thinking, huh? You see? You have to be a little bit smart. And we saw the same for the network size estimation, huh? So the idea was very simple there, huh? 1 node is 1, the others are 0. You calculate the average. The average is 1 over n, and then you just flip it. That seems very easy. But getting it to really work needs a little bit more thinking, okay? So the gossip is good to start, but you have to do a little bit of thinking to really get good. But it's possible. You can get really good. So this algorithm works really well, the topology management, if you do it like that. Okay, so conclusion on this one, it converges quickly, logarithmic, scales well. So they simulated up to 1 million nodes, and it's robust. If nodes fail, it just keeps going, you know? And so it's gossip, but it has 2 phases. Rapid convergence and endgame. And you see why you need these 2 phases, huh? You have to switch from one to the other. And you have to do, you can't do them naively, you have to do some little bit smart optimizations. But if you do that, it works very well, okay? So distributed systems that need topology, like distributed databases, they use these kind of gossip algorithms. Usually they're not doing 1 million nodes. If you have a cloud database, they will use a small gossip algorithm to build it up, okay? But bigger systems could do it too. And here's the final graph on this one, the final graphs, on different kinds of topology. Binary tree with different values of C. So the thicker lines have bigger C's, huh? Ring with different values of C, torus with different values of C. So basically, when it gets thicker, that means the C is bigger. You can see when the C is bigger, it's faster in number of cycles. But the messages are bigger. So no free lunch, huh? If you want it faster, you have to send more data. Fine, okay? But if you want very lightweight messages, then you'll be a little bit slower. And you can see it goes down very fast until the very end. You have this like weird step function, huh? Those are the stragglers. The stragglers are hard to get rid of, huh? So these are individual stragglers. It goes down 1 step, another step. So here we have 1, 2, 3, 4, 5. Here there's 5 nodes that are wrong out of 100,000. It's not very many, but you want 0 nodes wrong. Okay? So getting rid of these little stragglers is harder, but they are basically routing. That's why it takes many cycles, huh? This one here, there's 1 here, node left, but you still need, I don't know, 4 or 5 cycles for it to get to 0, because that wrong node is basically step by step moving to where it should be, huh? But we can't do better than that, huh? Because each node only knows its neighbors, huh? Can't immediately hop to the right place. Okay? Okay? Here's the convergence factor. So this was the factor that theoretically was equal to 2. So you can see, again, the the heavy ones. Sorry, here's the different sizes. We have small, medium, large networks. Small, medium, large. Small, medium, large. So the large one is 1 million nodes. The small one is 10 to the 14, 16,000 nodes, okay? So the large one, because there's many more nodes, when you pick randomly, when you double, it can double for a longer time. You can see it's doubling for a longer time before it goes down. Then the 100,000 nodes is quicker. It doubles less number of cycles, and the 1 million nodes is even, the 16,000 nodes is very quickly saturated. So that's the simulation result. So that is T-man. That's a nice, smart gossip algorithm with some cleverness in there. Okay, before the break, let me just finish with something which is more like a fun, different thing. This is the synchrony in nature. So in nature, we have synchrony. We notice it among living organisms, like pacemaker cells. So your heart has a bunch of cells that are making the heartbeats. Well, they're somehow synchronized. Or fireflies, or crickets, or menstrual cycles. If you have an army of women soldiers, they're going to be synchronized, okay? So this is weird. So how we can model it using gossip. And this is called the coupled oscillator model. So each little actor, each firefly, has a little oscillator and it flashes. Have you ever seen fireflies in trees? It's kind of neat, huh? They're not, I don't usually see them in Belgium, but sometimes you see them in tropical countries. So each one flashes, and it's independent. But they are somehow connected. Well, through the environment, but the fireflies, they can see each other, but it could be pressure or mechanical or smell, olfactory. So each firefly has some neighbors. So it's like a gossip network. So here's the firefly case. This is observed. Certain species of fireflies, seems to be only the male ones, because they're supposed to be doing it to find mates. Luciola pupilla is the Latin name. So they synchronize the flashes. So the whole tree is flashing. Pretty amazing. So how does it work? Well, each firefly has a small number of neighbors that it sees. And it's not instantaneous, because when it sees a neighbor, it takes some time. Each firefly has a little clock inside, and the periods are kind of random. So how does it work? Well, we can model this using our gossip algorithm. So each firefly is a node. It's only push, because the firefly will only say things to the neighbor. And the state is the phase of the local oscillator. So the oscillators have random phases, okay? And you have your neighbors that appear. And the update is when a firefly sees the neighbor flash, it resets its oscillator on the flash it sees, okay? But that will not immediately cause synchronization because of delays. And the other one does the same thing. So there's some kind of a funny behavior. But each firefly will reset its oscillator based on the phase. And then you can then you can simulate this, and you can see that it corresponds. It depends. The nature case, there's lots of variations, but it can correspond to the real nature case. So here is the periods. So you see this is a very small range, from 0.85 to 1.15 seconds. You can see in the beginning it's kind of messy, and then it kind of slowly converges, and they're all synchronizing. After a certain number of microseconds, a few seconds, they start synchronizing. Pretty amazing, isn't it? So that's a natural example of gossip. Okay, I stop there. So that ends the part on gossip. So now we do break, and after the break, I'll show you another neat thing, which is BitTorrent. Content distribution. This is another kind of gossip. Also a kind of a gossip algorithm that is a little bit more complicated than the usual, but it's still a gossip with neighbors, okay, and doing stuff. And I'm going to show you, first I explain what is the problem that we want to solve, and we want to distribute content to many people. So this would be like movies or files or something. And then I show you BitTorrent. So BitTorrent is a very famous algorithm that was invented a number of years ago and still widely used in many variations. Okay? So the problem is the following. I have a bunch of users, thousands or millions, and I have a source, a server, but it has limited bandwidth. And I want everybody to get a copy. That's the content distribution, okay? As fast as possible. So how do I do it? Okay, one way. So yeah, there's one way to do it. I'm very rich. I buy a lot of servers. And so I have enough servers so I can send information, and each server has a copy. Right? That's a solution, right? Yeah? That requires money though. So this is, there are companies that make a lot of money doing that. Major websites do that. This slide was done in 2007. In those days, the major content distribution guy was a company called Akamai. So I wanted to see who's the biggest guy today. Today, 15 years later, it's still Akamai, number one, but there's a lot of competitors. Amazon, CloudFront, Azure, CDN, CacheFly, Cloudflare, Google Cloud CDN, blah, blah, blah. So there's lots of companies doing that. But, of course, it requires money. And so we're going to look at another solution. The solution is that all the customers are going to cooperate. In the previous solution here, the customers don't talk to each other. They only talk to the big guy. Okay? But in our solution, the customers are going to cooperate. And this is used also in distributing software. So the example is Fedora Linux. So this is very good. So let's show how it works. Okay? So I want to show an example. So here's a user. It has a download bandwidth and an upload bandwidth. Okay? I have a server which can upload at 1 megabit per second. So today you have to multiply this by 100. Okay? But in those days, 16 years ago, this was reasonable. But otherwise, it's exactly the same. Okay? And you have 4 guys, each one downloading 256. Okay? But you're not always able to use it. Sometimes you're going to use a fraction. But let's say we have 256 to download. Okay? Because it might be asymmetric. So, okay. Fine. I have a 1 gigabyte file. Nowadays, this would be 20 gigabytes. Okay, 2 CDs. Nobody uses CDs or DVDs. They're so small, only 4 gigabytes, nothing. Okay. So, okay, you want to get a file of 1 gigabyte. So, how long for one user? 1 gigabyte, 256 kilobits per second. Okay, so 2 to the 23rd kilobits. Okay, kilobits, so 2 to the 20 times 3, 2 to the 8 kilobits, that's 2 to the 15 seconds. That's 30,000, 32,000 seconds. That's like 9 hours. See, those days, the internet was just bad, huh? Okay, but question. This is one user. For one person, can we make this any faster? So we're not out to improve the performance of the internet. Can we do some smart technique? Can we make it faster? What do you think? For one person. Later we'll look at many people, but for one person, no, huh? This is kind of the limit. Huh? You can't make it faster. You have a 1 megabyte and you only can get 256 kilobits per second. You have to wait. Okay? So, continuing. So we have the same server, which has, remember, it has a 1 megabit bandwidth per second, and each client receives 256 kilobits. That means I can handle 4 clients at the same time. Okay, fine. So let's say 1,000 people want that file. After 9 hours, 4 will have it. After 18 hours, another 4 will have it. After 27 hours, another 4. That's very bad, huh? After one day, there will be 12 people who have this file. Not good, huh? So content distribution does much better than this. Okay, so how does it work? So look at the situation. We have 4 people sitting in their house waiting for a movie. The movie is sitting here and want to download. Now, there are resources here. And we're not using all the resources so far. And the question, where are the unutilized resources? This is multiple choice. The upload of the server, the download of the server, the upload of the clients, the download of the clients, or maybe there are no. Maybe we're using all the resources already here. So what do you think? Where are the unutilized resources? Are there any even? What's the right answer? So I'm using the arrows, okay? I'm using the colored arrows, but are there more resources that I'm not using? What do you think? Are there more? Or not? Maybe not, huh? Maybe the answer is E. There are more, right? Come on, speak. Yeah.
The users can communicate between each other?
Yes, the users can communicate between each other. So the users have also, the clients have upload bandwidths that is not being used here. So this user can talk to this user. So that's a resource that exists and that we're not using. So let's use it, okay, and see what we get. Okay, let's take a step. I want to introduce a concept called a piece. So when we want to send a big file, we're going to slice it into little pieces called pieces. Let's say 256 kilobyte per piece. Okay, so if each client has a download bandwidth of 256 kilobits per second, how long does it take to download one piece? Well, it takes 8 seconds. Huh? If the download bandwidth is 64 kilobit per second, ooh, very bad, huh? 32 seconds. Okay, see how bad the internet was in those days, huh? And in the 90s it was even worse. Okay, so here's a possibility. Okay, so here's a server. Here we have 4 clients, and here we have 4 more. We're going to use some upload bandwidth. Here we have a second scenario, 4 clients and 4 more. So here, this client is getting the first piece. So how long does this guy have to wait until he gets his first piece? Well, 8 seconds, right? 256, so we're the same speed. Okay, so 8 seconds, yeah? Let's compare the other guys now. This guy, how long does this guy have to wait until he gets his first piece? Well, he waits 8 seconds until this guy gets the first piece, and then it's sent from this guy to this guy. So basically 16 seconds. Okay. So in this scenario, each of these yellow guys will get the first piece after 16 seconds. Okay? So what about the second scenario here? Well, now all these four guys are connected to the same guy here. So each of these guys, how long do they have to wait? Well, 8 seconds until the blue one, plus, because it's divided into 4, they have to wait 32 more seconds. So they have to wait 40 seconds. So here it was 16 and there was 40. So the lesson here is who you connect to is important. Okay? The four guys connecting to the same, not good enough. So the lesson is, so 16 compared to 40. So this is bad, and this is good. So the decision of the yellow guy, who to connect to, can make a big difference. Here they're all connecting to the same guy, it's not good enough. So that's leading to an intuition. So there's two concepts, which I call peer selection and piece selection. So that's important for the algorithm. That'll be important for BitTorrent. Peer selection is which client you talk to. Okay? From the point of view, so the clients are called peers. Peers because they're all running the same software. It's not client-server, they're all equal, so they're peers. Okay? So each peer will connect to another peer, and I just showed you selecting the right peer is important. It can make a big difference in performance. Okay? So selecting the right one to connect to is important. Right? You see that, huh? Okay? Okay, another intuition. Okay, here we have this guy talking to these four guys. Okay? So now I have four upload links, 64 kilobits each, and now these guys are talking to each other, like this. Okay? So each one of these guys will be downloading from 4 and uploading to 3. Okay? Total download rate, maximum 256 kilobits, total upload rate 192. Okay? Now we have another intuition here. It's not only the choice of peers, it's the choice of pieces. So let's say we have now again two scenarios. So each of these guys gets piece number 1. Fine. Okay. So, and now in the second scenario, this is piece 1, piece 2, piece 3, piece 4. So, if each of these guys gets piece number 1, then they have no information to exchange to each other, right? Okay, so this is the final slide. So here, if they both get piece 1, then that's it. They have to wait for piece 2. But here, we have a different behavior, This one can get piece 1, this one get piece 2. Once this one has piece 1 and this one has piece 2, piece 1 they can send it here, piece 2 can send it there, and it can be done concurrently with piece 5 and 6. So if the clients have different pieces, then it can do better because they can get different pieces at the same time. Okay? So the second scenario is better. Okay? So that's another conclusion. Piece selection. So a peer will connect to a client, that's peer selection, but it will also decide which piece it downloads, you see? So that's important too. So when we define an algorithm, we need to understand how to do peer selection and piece selection. You see that? Those are the two important insights you have to understand. And BitTorrent will give a solution to that, but in general that's the thing you have to do. Peer selection and piece selection. Okay? Okay? So we know two things are important. Selecting the right peers and selecting the right pieces. So we need to make an algorithm that does that. Okay? and maximizes the utilization of all the resources so everybody gets stuff as fast as they can. Finish the download fast. That's very reasonable, huh? So this is what we want to solve, okay? So the algorithm that we design has to do peer selection and piece selection in the right way. Okay. Okay, so this is the problem. Given a set of peers with known bandwidth, give a schedule listing all the connections between the peers and specifying which piece should be transferred. This is like once we know the whole setup, we can compute the schedule and make an optimal solution. Yeah, but that's not really going to work in a big system, huh? If we have a small fixed set of peers with fixed pieces, yeah, fine. But in a large and heterogeneous system where peers are coming and going, it doesn't work like that, okay? So you can't, so this is a hard problem. Computing a schedule for all peers to download optimally is NP complete. Fine, it's a hard problem, okay? And in any case, we can't really do it in a centralized way. Who will enforce it? Nobody can enforce it. All the peers are running independently. So we can't really do an optimal algorithm, and we can't do a centralized version, okay? So there's two ways to look at the problem. This is a typical peer-to-peer reasoning, huh? Either you have global knowledge or you don't have global knowledge. There's a central authority or there's no central authority. And as you are understanding now in this course, distributed systems are kind of evolving towards this, the no global knowledge case, okay? The newer systems are all removing the need of global knowledge. Gossip has no global knowledge, okay? The smart shared memory algorithms have no single server. The consensus algorithms have no single centralized node. So this is what we want to do. There's no global knowledge, okay? So that's one thing. It's completely decentralized algorithm. Every node is running a piece of code, and nobody's controlling it. It's very nice, huh? So the gossip was already doing that, huh? But now we kind of bring it up front. We really want to see, this is how large distributed systems actually work, huh? The big ones from the second part of the course, there's going to be no global control. And it's not just that. Things are changing always. Peers can crash, new peers arrive. Also, peers are selfish. Once I have downloaded completely the file, why do I need to stay connected? I have the file, I go away. So you don't really want that, because then the others get a disadvantage. So you need to solve that problem, also bandwidth shading. So you have a very dynamic thing. So this is the algorithm we're going to show you, an algorithm that works in this very dynamic situation, okay? So this simple solution, a central peer knows everything, and it makes decisions that won't work, huh? Okay? Okay, but you want something more like this. You have some weird random connection. It's like kind of like gossip network. Peers are kind of randomly connected, and a peer will choose a random piece. This is more reasonable, okay? But still, it's not good enough. So this is going in the right direction, okay? Each peer somehow is randomly connected, and the peers are kind of choosing random pieces, and then it sort of works. But that's not good enough. But that's the starting point, okay? Okay, so this is now moving into BitTorrent territory. Okay? And BitTorrent is very interesting because there's some economics ideas behind it. In a free market, everybody is buying and selling, and everybody should profit. If I buy something, I should be happy. If I sell something, I should be happy. Everybody should be happy. So there's this notion of everybody is being happy, satisfied. So BitTorrent is kind of in that territory. Okay, so some history. BitTorrent is coming from 2005, and it made a huge impact when it first arrived. It blew everything away, because nothing like this existed before. So it was invented by a guy named Bram Cohen, and then they have some phrase, movie studios hate it, sure, file swappers love it. Bram Cohen's blazing fast peer-to-peer software has turned the internet into a universal TiVo for free video on demand. Click here. So TiVo is a device that was attached to TVs that made the TV programming completely flexible. Okay, so now let's go start talking more about BitTorrent. So it has some terminology, which I should introduce here. Funny terminology, but it's partly coming from economics. You'll see there's seeds, there's leechers, there's trackers, torrent file, meta-info file. There's a concept of choking, unchoking. Rarest first, tit for tat. Tit for tat is a way of encouraging good behavior. Pareto efficiency, that's a concept from economics, where everybody's happy, okay? That's what you want. So BitTorrent tries to get that. So let's introduce now the ideas. I think you're curious to see how this whole thing is going to work. So seeds, a seed is a machine, a node that has the complete file. So I have a file, I'm a seed, okay? But I get the file, but once I get it, maybe I want to go away, okay? So they're kind of selfish. But in order for this whole thing to work, at least one seed has to stay long enough to serve to send out a complete copy of the file. So there has to be some minimal non-selfishness. So BitTorrent has some incentives to help this. And in the whole system, all the pieces are kind of all over the place. But all the pieces must be there, or else it doesn't work. But that's usually not hard. So that's a seed. On the other side, you have leechers. Leechers, it's a great word. In French, sensu, so a bloodsucker, if you want. So any peer who does not have a complete file is called a leecher. So the leecher stays a leecher until the leecher gets the whole file, and then the leecher becomes a seed. Once you get the whole file, you're a seed. Okay? So you have seeds and leechers. And you have a third kind of node called a tracker. A tracker is just kind of the way to get into the system. It's a peer that tries to keep track of who are the seeds and who are the leechers. But not all of them, but some of them. You can have multiple trackers. So it's not really controlling anything, It's just a way in. So you keep track of some of the seeds, some of the leechers. So how does it work? Okay, so now we go into how the algorithm works, BitTorrent. So I showed you some things already. So seeds, leechers, and trackers I mentioned already. Now let's go to the next guy. There's this thing called the torrent file, or meta-info file. This is kind of a way of getting into the system. So I have a file. I want to share it. What do? So I'm here. I have The Mask of Zorro, 1 gigabyte, really good movie. I recommend it for you. You create a meta-info file, and you send it to the node, which is the tracker. Okay? And the tracker knows some peers. And the next step is you put it on a web page or send an email. It has to be kind of published, disseminated. So you need this mechanism. So web pages are nice because they have text and they are publicly accessible. There's a protocol, HTTP, anybody can access it. So putting on a web page, sending it in email is a way of publishing it, okay? Once you have that, now the tracker knows it, so the leechers, okay, will get that information from the tracker, and then they start doing things. So that's the way to get into the system. If I want to start disseminating a file. Okay. Okay, so the tracker. Okay, so I have nodes, and the guy who wants to disseminate the file needs to know some peers. So the trackers, the only rule really is to know some peers. So H, so this is the new node, it says get peers. And the tracker will tell me about some peers, but just a subset, not just some of the peers. Typically 40 peers, for example. The tracker will tell me 40 peers, and that's all really the role of the tracker. It has to have some information about what's going on. So it's a way of getting into the system. Okay, so now I know 40 peers. Okay, so the new guy H, once the new guy is in, the new guy sends a handshake message to the 40 peers. That's basically telling the peers, I exist, okay? So that he knows, so that all the peers know the new guy. Okay, so the new guy is now in the system. Okay, good. And what happens now? Now we start sending information about the files. So a big file is made out of pieces, 256 kilobytes, for example, per piece. So the file is represented by a bit vector, and each bit tells me whether I have that piece or not. So if there's 100 pieces, it's a bit vector of 100 bits telling me whether I have the file or not for the new file. Okay? Fine. So the new guy sends this one, but this one will have, if it has the full file, it will be all ones. So it says, I have this guy. So if it's all ones, then I'm a seed. Okay? But usually it won't be all ones later. And the other guys will send me a bit field back. If I have nothing, it'll be all zeros. If I have I don't have anything. But later on, when they're running, it'll be changing. So they exchange bit fields. So that will be going on a lot. Okay? Okay, because the bit field is not just the file that you upload, it's all the files that are owned by the leechers. Okay, the leecher might have 25 pieces of Star Wars, A New Hope, and it might have 32 pieces of some other movie, the first Superman movie, whatever. And so every leecher knows exactly what the other peers have. It knows the pieces. Okay? So here's two nodes. Each node knows what the other peer has, but this link, there's 2 bits attached to this link. So this is the node between leechers. Some of them might be seeds, but it's between 2 nodes. There's a link. And on this link, on each side, there's 2 bits. One of them is called choked, and one of them is called interested. Okay? Interested, they're both booleans. Am I interested in some of the pieces of node B? If I am, then interested will be true. Okay? A is not interested in B's pieces. I don't need any of your pieces. And choked is whether I'm uploading to B. So if B is choked, that means I'm not sending anything. So choked is true means A is not sending anything to B. Okay? And here B, choked is false. So B is willing to give to A. B has unchoked A, so B wants to give stuff to A. B is also interested in A's pieces. Interested in true. B thinks there's some pieces there that I want. Okay? But if nothing will happen yet because A is not interested. But maybe the state of A will change in the future. Okay? Okay, so that's how the link is annotated. So you have these choke, and interested. So interested is true or false. depending on the bit fields. So the bit field is telling me which pieces that the other guy has, that I get the bit field. I say, am I interested in some of this? That one has piece 13, I don't have it, I'm interested, okay. Choked, initially true. So when a new node comes in, you don't send anything. But maybe, if I'm interested in somebody, and that person unchokes me, that means he's willing to send to me, then I can unchoke him. So maybe, it depends. So you see, the choke is a back and forth. If someone unchokes me, I can unchoke them. If someone chokes me, maybe I choke them. So it's kind of what's called tit for tat. If someone cheats to me, I will. If someone says, I don't give you, then I don't give back. So if you want somebody to give you a piece, you have to be willing to give them a piece. You see? They're mutual beneficial. So the selfish node can only get a piece if it wants to give a piece. You see how we're encouraging the selfish nodes to do things, huh? So that's the idea of the choking. Okay? So okay. Now the actual piece selection. So assume you have the two nodes, they both unchoke each other, so they both want to send pieces. Which piece are they going to send? Okay, there's three policies. Rarest first, random first, and endgame mode. So rarest first is the piece that is rarest among all the peers I know. That's very important. If it's a rare piece, I should ask for it, okay? Or random, or endgame. Endgame is when I only have one or two pieces missing. It's kind of like the T-mana. When I'm almost done, then I have to change the approach, okay? And sometimes you divide pieces into small pieces, but we'll see that, okay? Rarest first is choose the piece that is rarest among your peers. Okay? That's actually the most reasonable policy. If piece number 13 is very rare, you better get your hands on it before it disappears. Okay? So if only one peer has piece 13, but many peers have piece 17, then you're going to ask for 13. And that's good for many reasons. It means if very few have piece 13, once you ask for 13, you also have 13. So more will have 13, so that's good. Also, if that 13 guy is very selfish and goes away, if there's only one guy having 13, then there will be no more 13. So it's good if there's more than one. So rarest first is a good piece selection. Okay? Rarest among your peers. Okay? So that's the thing you do normally. But in the beginning and the end, you do a little bit different. Okay? In the beginning, you will do random first. So in the beginning, you don't care about the rarest. You want to get a piece very fast. Okay? You want to get pieces really fast. Get first piece as fast as you can. Even if you have to divide it into sub-pieces. So they have, actually, pieces can be divided into sub-pieces to get it even quicker, okay? So, in the beginning, you want to get pieces very quickly. So you don't care if they're rare or not. You just want some pieces, okay? So that's the beginning. And at the very end, your file is almost complete. You have a few pieces are missing. So you ask specifically for those pieces. You don't care if they're rare or not. I need piece 15. It's the only one I'm missing. I don't care if it's rare or not. That's the one I need to complete my file. Okay? So in the endgame mode, you ask for the pieces or the sub-pieces that you need. Okay? Now the choking, like I mentioned before, this is two peers talking. So you're punishing selfish user. If a selfish user is choking me, I will choke them. So I punish them. This is called tit for tat. Tit for tat is a way. But it has no memory. If they unchoke me, I unchoke them. So tit for tat, if someone is selfish to me, I punish them, but only once. I don't remember, I forget. If they start behaving nicely, then I will be nice again. So if they choke me, I choke them. But if they unchoke me, after I unchoke them, there's no grudge. No grudges are held. Okay? Works very well. This is called tit for tat. Okay? And the idea, there's actually an idea behind this. This is called Pareto efficiency. This comes from economics, so you can look it up. So a system is Pareto efficient if you cannot change resources. So you have a bunch of people and they have resources, and you cannot switch the resources. That both will get happier. You cannot make them happier. They are as happy as they can be already. Okay. So because of the local, so this is a global optimum Pareto efficiency, yeah. But you get it through local operation, through the tit for tat, choke and choke, that leads to a Pareto efficient system. That means everybody will be happy in this kind of system. Everybody will get to file. So that is kind of more theoretical. That is kind of the reason behind why it's good, working well. Okay? Okay, so choke and choke. Okay, it depends on download rate. It means if somebody is sending me stuff, I unchoke them. But if they don't send me, so I'm choked, I choke them. But still there's a limit, because it's hard to handle many. So the unchoke limit is 4. So out of my 40 peers, I'm actually only unchoking 4, and I regularly recalculate. And I look at the download rate. If some node, I've unchoked them, they're sending me stuff, but now they slow down a lot. That's not nice, they're selfish. Well, maybe I choke them then. I punish them. But if they start sending me, then later on I can unchoke them again. Okay? So how can I unchoke them once they choke me? Because there's some randomness here. Okay? So it's like this. So let's say I have 80 connections, 40 outgoing, 40 ongoing. I only unchoke 4 peers, and the decision on unchoking is every 10 seconds. So 3 of them are unchoked depending on how fast they give data to me. They upload, I download. So if they send me, this is show me yourself policy, is kind of a slogan. It means if they send stuff to me, I send stuff to them. But there's one unchoked is randomly. So if somebody chokes me and I choke them, and then that person says, oh, that's not good. Well, he unchokes me and starts sending me information. But I still have choked them. But if he sends me a lot of information, I can unchoke them again. And then he's happy because he's getting information from me. So the idea is, if someone behaves badly to me, I punish them. But if they start behaving well to me, I reward them. See, so that's the way that selfish nodes are handled. And it works very well. Okay, so this works, this system. Okay, so that is, so the optimistic unchoken. So there's some magic numbers here. I don't know if it's still 30 seconds. So you can rotate every 3 seconds, whatever. So this is magic. I'm not going to say much. Okay. Okay. So then there's some tweaks. When I have everything, I will only upload to fast guys, and not to slow guys. So concluding on this, so the algorithm, so the 2 things are piece and peer selection. So the piece selection, remember which piece, while it's running, it's mostly rarest first. So among all the pieces that I need, I pick the one that's rarest among my peers. That's best. But in the beginning and the end, I do something different. Okay? And then there's peer selection. So there's the start, the construction of the list, when you get in the system, so that's with the tracker. And then there's the choking, unchoking. So this is the algorithm we saw. Which guy is sending me things faster? Well, I tend to unchoke those guys. But if they send me slower, I choke them. But if they start sending me faster again, I can unchoke them again. Okay? So there's a very interesting algorithm for choke, unchoke. I'm doing what's called the tit for tat. Okay? So that is how BitTorrent works. Okay? So you see the idea, you see how it handles selfish nodes, you see how it has an endgame mode, start mode, and this algorithm, of course, was tweaked. All the ideas I'm telling you were added because they make it work. Huh? So this algorithm works very well. Okay, so now that's all for BitTorrent. There's another thing about firewalls, which I won't say much. You may have seen this already in the network course. Network adverse translation means something to you. It means that nodes are often not publicly accessible. They are sitting behind something called the network address translator, and they have their own little IP address, and you can't just connect to them. You have to somehow go through the network address translator. Okay? So that has nothing to do with BitTorrent, so there's algorithms for that. There's an algorithm called stun, UPnP, it's called NAT hole punching, basically making a connection to a guy behind the NAT. So in practice, to make BitTorrent work, you have to handle the NATs and the firewalls. So the NATs, which are part of the firewalls, you have to handle that. Because the nodes are not always publicly accessible. So if you want to make a practical BitTorrent algorithm, especially nowadays, a lot of nodes are behind the NATs. Okay, so that's it. Okay, I have explained it. So that's all. So what do you think of BitTorrent? It's nice, huh? It's essentially a gossip algorithm, but very cleverly made. And you notice the end game idea is in both of these, the T-Man and in BitTorrent. And you note that the tit for tat idea, if I want something, I have to give something first. That works very well. And if I start being nasty, if I stop giving, then I will stop getting. But if I start giving again, then I will start getting again. There's no memory. That's very important. The algorithm does not hold a grudge. So that's actually a good policy for humans also. If someone is nasty to you, the idea is to be nasty to them, but only once. But if they want to repair and be good to you again, you start being good to them. No grudge. That's the best. So economically, that works very well. Okay, so let me stop there.